Today we'll be talking about the global energy balance. You'll see a lot of diagrams like this particular set of diagrams that go back, in this case, to 1917. There's a lot of them out there. Mind me, people can make things more confusing than they need to be. So we're going to just take a cursory look at these in this course. We're not going to focus on them. Don't bother memorizing them. The inputs and outputs can be confusing because they don't add up to 100%. And there's a lot of other issues with them. Don't worry so much about these diagrams. Some things that are important to know concerning the global energy balance include: what are the basic characteristics of electromagnetic radiation? What causes the greenhouse effect, and how is the magnitude of this effect determined? How do clouds affect the atmospheric radiation budget? What are the most fundamental feedbacks in the climate system? These are things that we'll be discussing over the next several lecture segments. So here we have a couple neighbors in space, Earth in the center, obviously. To the left, the planet Venus. To the right, the planet Mars. These planets are going to differ at their surfaces largely because of the differences in the way electromagnetic radiation is received and redistributed on these planets. Starting with Venus, here we have an original Mariner 10 photograph from 1974 on the left, and a recently reprocessed image from the same data on the right. So we're revealing a lot more information in this newer reprocessed digital image. If we strip away the clouds, the water vapor that makes up the clouds, this is the surface of Venus. This was an image taken by overlapping probably hundreds to thousands of radar images of the planet Venus's surface, meshing them together and revealing the complex tectonic history of the planet. Here we have the planet Earth as we see it today, centered on South Africa, which you can see right here. Madagascar located over here, home to the penguins. Eritrea, the Sahara, the Saudi Peninsula here, Europe just off to the screen to the top. So the most notable thing we observe in looking at this particular image is the color blue with a considerable amount of white superimposed on top of that blue. Now, both of those are part of the hydrosphere, the water that we find on the Earth's surface. If we were to strip away that water and produce a sphere with it, what you'd see is an image something like this. Here we have all of the water on the Earth's surface and within the Earth, and making up the ice caps and the ice sheets, etc. All water is represented by this sphere, which is nearly insignificant considering the size of the Earth as a whole. This sphere represents liquid fresh water. This includes surface water, rivers, lakes, streams, ponds, etc., plus groundwater that's easily accessible. And this tiny, tiny sphere here represents fresh water from lakes and rivers. This is all of the water, for the most part, that humans have available to them for consumption. This is the planet Mars. We didn't need to strip away the clouds because they're no longer present. It says here the water was removed naturally, and that is due to a couple differences between Mars and Venus and Earth. One is the size of Mars. Because of the ultimate size, the surface to volume ratio, plate tectonics slowed and then stopped long ago on the planet Mars. This influences, as we'll see, the magnetic field of the planet, and essentially it goes away when tectonics stops. That helps shield the atmosphere from space. Without that shield and without the mass of a larger planet, the atmosphere is simply wisped away over hundreds of millions of years. And what we're left with on Mars are some ice caps that are composed predominantly of carbon dioxide frozen here at the pole. And we believe there's going to be some water trapped within the soil, within the regolith on this planet. One attempt to find out the nature of this water, perhaps how much water was once present, and importantly for us, did that presence of water lead to generation of life? So we're looking at a couple features here. One is a crater. You can see here, you may have seen this in the news recently. It's a new target for NASA for a future space mission. It's clear to a geologist, at least, the features represented here within the crater are probably deltaic. So this indicates that water moving along this channel, this canyon, was carrying sediment. And when that water entered a lake that filled this crater at some point in the past, that sediment transport slowed, and ultimately the sand, silt, and mud grains would sink from that water column and be deposited here in what's more or less a bird's foot delta. You can see it a little more clearly here in this image that's been false colorized. This bird's foot delta looks very similar to the modern Mississippi River Delta that you see just to the south, for the most part to the south of New Orleans today. So it's an ideal area to look for water and to look for signs of life. Now, the Earth has a mean surface temperature of about 15 degrees centigrade, or close to 60 degrees Fahrenheit. Venus, on the other hand, about the same size as Earth, and nearly the same distance from the Sun as the Earth, has a surface temperature of 460 degrees centigrade, much warmer. And that translates to about 860 degrees Fahrenheit. Mars, on the other hand, has a temperature of minus 55 centigrade, or minus 67 Fahrenheit. Now, every 10 years or so, we get down close to that temperature here in Saskatoon. Last year, I believe we get down to minus 53 or so. So that gives you a rough idea by walking outside in February what it might be like on Mars today. The question is, are we just lucky here on Earth? Are we in the right place for liquid water? That's going to be very important for controlling our climate system and for giving us the ability to live, to support life forms on the Earth, from microbes up to the most complex creatures. So here we have a pressure temperature phase diagram in which water is represented by this field, water vapor is represented by this field, and water in the form of ice is represented by this field. Now we're pretty close in terms of temperature to this triple point, and this is why any given day in the spring or fall you might see liquid water on the ground with some ice, and we know that there's water vapor in the atmosphere because we can measure it. That's our humidity. So fortunately for us, it sounds like the Earth is not too hot, not too cold, but just right. And you may remember this from a fairy tale. We all know that the Earth is heated by the sun, and we now, thanks to this slide, know that the sun emits about 50% of its energy in the form of visible light. Is this a coincidence? Probably not. We probably evolved our vertebrate eyes to capture this most common series of wavelengths that are emitted from the sun, and we call that eyesight. We have evolved the ability to see this incoming radiation, at least a lot of it. We can't see the extremes. We can't see the longer wavelength radiation that we use for communications, like cell phones, and we use to heat food, microwaves, or that we feel as sensible heat. You walk outside in the summertime, you can feel heat rising from, say, a hot black parking lot. That's sensible heat. That's on one end of the spectrum with long wavelengths. On the other end of the spectrum, there's ultraviolet radiation. Now, we can't see ultraviolet radiation, but other animals can. Animals like insects and probably some birds can see this ultraviolet radiation, and they use that to their advantage to find food, for migration. They're using wavelengths of light that are invisible to us, which explains potentially why they have some of these mysterious behaviors. It's not mysterious for them. They can see where they're going. We can't see where they're going. If you're into photography, as some of you may be, you'll know that different types of lighting produce different wavelengths of visible light, and you need to compensate for that difference in wavelengths in adjusting the white balance of your camera. That white balance is going to be tuned in to the source light wavelength group. In this case, noon sunlight broadly spans the visible spectrum, as you might expect. Tungsten lamps, which are used commonly in photography, are going to be at the high frequency or short wavelength band, so you need to compensate for that in adjusting your white balance. White LED lights, you can buy white LEDs that produce light predominantly at a range of wavelengths, and you'll choose your wavelengths, again, depending on your photographic needs. Or say if you're raising plants in your house, you want to choose a light that's going to emit radiation that's beneficial to that plant. Other examples that are common in our world include mercury vapor lamps. These are the kind of orangey, yellowish street lights that are common around the world today. They emit specific bands of wavelengths of radiation, and that's because of the nature of how they're produced using mercury vapor. When you go to the store and whatever you're purchasing is scanned, we're using this wavelength of light. Now, in discussing electromagnetic waves, there are a couple of things to consider. Most importantly, perhaps, at least up front, properties of electromagnetic radiation. A self-propagating electric and magnetic wave. All such waves move at a constant speed, c, which we refer to as the speed of light. The wavelength is the distance between two adjacent crests, or troughs. Now, this would be a crest, this would be a trough. Subsequently, there's another crest and yet another trough. The distance between this crest and this crest would be a wavelength. The distance between this trough and this trough would also be a wavelength, known by the Greek letter lambda. The speed is going to be consistent regardless of the wavelength. It's always going to be denoted by c, the speed of light. The frequency is the number of waves that pass a point in 1 second. This is denoted by the Greek letter nu, which looks like a little v. So this is a frequency. We list frequencies based on the amount of waves that pass in a given time. In this case, the time is most commonly, if not always, a second. The speed of the wave must be equal to the product of the number of crests that pass a point each second. That's the frequency, the number of crests that pass a point each second, and the distance between the crests, which is known as the wavelength. So we can describe that here as lambda nu being equal to the speed of light, or c. This means the longer the wavelength, the lower the frequency. This has important implications for us in our world today, as you'll see. This changes the equation somewhat, or rearranges it, such that nu, the frequency, is equivalent to the speed of light divided by the wavelength. Photons are another way that electromagnetic radiation behaves. It behaves as waves. It also behaves as particles, or streams of particles that are known as photons. Photons are, by definition, the smallest discrete unit of energy that can be transported by electromagnetic waves of a given frequency. The energy of a photon is proportional to its frequency, such that E is equal to h nu, where h is Planck's constant, defined down here. That is in turn equal to Planck's constant times the speed of light divided by the wavelength, lambda, here. Where am I going with this? Well, we can take a look at some real-world, fairly simple examples. For our purposes, what this means is that high-frequency photons have higher energy that can break molecules apart, whereas low-frequency photons cause molecules to vibrate or spin, either at a higher rate or a faster rotation. So this makes things appear or feel hotter. Now, the examples we'll use right now are a campfire. You approach a campfire, it gets warm, you sense that heat on your skin, if you have some exposed skin anyway. And you can also see some of the radiation being given off by that fire. Not much. Fires aren't really bright. You can look directly at them without any kind of eye damage, generally. A different example that we should be concerned about are X-rays. Now, X-rays are high-frequency, short wavelength radiation. For our purposes, very high-frequency radiation that will actually travel through our flesh, and it will go through bone as well if you make the X-ray strong enough. But generally, we're interested in soft tissue information, and in the case of broken bones, obviously we're interested in the harder tissue, how that is going to appear on an X-ray photograph, as in this. So the campfire can't do any damage to your cells. We now know that X-rays do damage to our cells. Here we have a page of properties of photons. I won't read this to you, but you'll have it here for some background information. X-rays. What's the deal with X-rays? Considered kind of magic when they were first discovered. As with many scientific discoveries, it was more or less an accident that they were discovered, and they were quickly put to use. And in this case, it was very common, particularly in North America, to go to a shoe store and have your feet x-rayed to make sure that you got proper fitting shoes. So here we see a commercial from a newspaper way back, probably, I'm guessing in the 1920s or so, maybe a little more recent than that, where people would go to the shoe store, insert your feet into this machine, which you can see here to the left, and they would blast you with some x-rays, produce a photograph, show you what your feet look like, all pretty amazing stuff, get you a pair of shoes that fit properly, and you're on your way. You do that a few times and you might develop cancer from these x-rays. People eventually caught on to that, and thankfully no longer when you go to a Foot Locker or wherever you go to get shoes, your feet aren't x-rayed anymore. That's an unnecessary risk. If you are injured, then x-rays are a necessary risk. They're much safer these days because we know more about them. We don't bombard people with the amount of x-rays we used to. So we've moved on. We've learned. Okay, so 5G. What about 5G? Conspiracy theories about this type of phone technology have been around for a long time, since mobile phones first became popular, but they go back much further. Doctors talked about radiophobia, fear of radio waves, as early as 1903, over 100 years ago. And subsequently, people became concerned about power lines and microwaves in the 1970s. They were mysterious to a lot of people and therefore scary. Opponents of 2G technology in the 90s thought that radiation from mobile phones would cause cancer. And of course, if there's some special information that's going to ruin somebody's business, the information is probably covered up. That's how conspiracy theories are generated and propagated. Other conspiracy theories about 5G include the idea that it was responsible for the unexplained death of birds and trees. Now, most of the deaths of birds and trees can be explained, so I'll throw that out the window. The coronavirus 5G conspiracy theories come in a couple different strains, and these range from, well, if I don't understand much about science, that might make sense, to I don't know anything about science, and that makes perfect sense to me. Modern 5G networks that are of concern use two primary frequency ranges. We'll call them frequency range 1. That's from 450 megahertz to 6 gigahertz. This would include the LTE frequency range. The other primary frequency range, which we'll call FR2, ranges from 24.25 gigahertz to 52.6 gigahertz. The sub 6 gigahertz range is FR1 and the millimeter range is FR2. Now, both of these groupings, or all of these groupings of radiation, are below that of visible light, in that their wavelengths are longer than visible light. So this radiation should be less dangerous to you on a cellular level than visible light. And if you're worried about radiation, you should not expose yourself to pretty much anything. So don't worry about 5G. It's all made up stuff. The fears are not real.